So thanks for tuning in. So this is going to be the second lecture on the origins of the solar system. And last time we talked about the patterns that we find in our own solar system and how we are also able to study other younger solar systems. And combining those two pieces of information, we can form some sort of theory about how our own solar system formed. And so, if this theory is sound in any way, then it should be able to explain why our solar system looks the way it does. And so, today we're just going to finish up that theory and specifically talk about how temperature plays a role in the structures or the arrangement of how planets are in the solar system, and also how planets were able to gain their first atmospheres. So let's just jump right in here. So turns out the temperature within the disk itself plays a huge role when it comes to being able to explain, why planets are arranged the way they are in our solar system. And so, simply put, the inner disk, basically the part that's closest to the sun, is a whole lot hotter than the outer disk. And so if you look at this picture here, this picture is showing you how the temperature is changing as you move further and further away from the center of the disk or further away from the star itself. And so you can see here that when you're relatively pretty close to the center, the temperatures are about 2,000 degrees Kelvin. That's about, I think that's 3,000 degrees Fahrenheit. And then it quickly drops off, becoming really, really cold. And so these are really freezing temperatures when you're basically up to here. And so this turns out to be the main cause of how the planets are arranged, because it will lead to a big difference in composition for the inner and the outer part of the solar system. And so when you look at the solar system, what you will find is that there is a strict divide from where rocky and metallic materials are found versus hydrogen compounds or icy materials are going to be found. So basically, within some sort of like imaginary boundary that's called a frost line, that is going to be the distance from the sun where hydrogen compounds can actually condense or can become solidified. So that's at about 50 degrees Kelvin. However, anything within that frost line, anything closer to that, then those hydrogen compounds actually stay in their gaseous forms, whereas rocky and metals can still stay solidified. And so when you actually measure theoretically how far that frost line is from the center of the solar system, that's actually about 5 AU. So keep in mind that number because we're going to go back to it later. And so here is just a picture that shows you the basic ingredients that can be found in our solar system. So hydrogen and helium, two basic elements. 98% of the mass that you can find in the solar system comes of this form. And so when you have hydrogen and helium very close to the center, they just stay in their gaseous forms. However, if you look at metals here, which, if you add them up, 0.4% and 0.2%, I mean, it's less than a percent. And that's actually enough material for you to be able to make all the planets in the solar system. Okay, so you can see that these are their temperatures. So these temperatures are basically the highest temperature that they can withstand, such that they're able to remain solid. So anything higher than that, then they're going to get vaporized or liquefied or go into a different physical state. So you can see that they're able to withstand much higher temperatures compared to these hydrogen compounds like water, methane, or ammonia. And basically what this means is that, 150 Kelvin, anything higher than that, and they become vaporized, they enter a different physical state. And so if you think about it, this is actually what composes the planets that are on the outer part of the solar system. And so now, if you think about that, now knowing that, hey, rocky materials can withstand the high temperatures closer to the sun, whereas hydrogen compounds can only live past 5 AU, correlate that with the composition of the 4 planets that are closer. So those are going to be the 4 inner planets, or in other words, the terrestrial planets. And then when we actually theoretically calculated the frost line, that was at about 5 AU. And so now if you think about it, well, Jupiter's orbit, the first Jovian gas giant, is located at 5.2 AU. So that physical limit, which is 5 AU, is what allowed Jupiter to form, like past that frost line. And so, and from there, you can say that, hey, because you have hydrogen compounds being able to condense past the frost line, then the 4 outer planets are going to be gas and ice giants. So you can see here's a little diagram here, by the way, where you have your first 4 inner rocky planets, so terrestrial planets. And, this is kind of a zoomed out picture in the very top panel. And they're all contained within this smaller orbit. And then past that, you can see that the 4 Jovian planets are much more widely spaced apart. And then in addition to the planets, this also explains why in the asteroid belt, which are these materials that are made up of, rock and metals, they're going to be in between Jupiter and Mars. Whereas in the Kuiper belt, made up of icy leftover materials, are going to be past Neptune because they're able to condense at those distances. And if you think about how planets formed from the last lecture, well, again, these are basically like the leftovers, the planetesimals that never actually formed. So a popular question that gets asked is like, hey, in the asteroid belt, let's say you have all those leftovers, is it actually possible to form another planet somewhere in between Mars and Jupiter? And the answer is actually most likely no. And the reason for why that is because if a planet were to start coalescing between Mars and Jupiter, well, Mars and Jupiter, they have very strong gravities, so they can actually pull that planet apart via tidal forces and preventing it to getting any bigger and forming another planet. Okay? All right. So now let's shift to a different topic here, but still related, talking about how planets were able to acquire so much gas. This is particularly very important when it comes to the gas giants, or the 4 outer planets in the solar system. And so the next step, after forming the rocky metallic planets and their cores, once you have that mass established, is to acquire gas from the accretion disk using their gravitational forces to pull them inward from all different directions. And so that's called core accretion gas capture. So it's kind of a mouthful, but basically core accretion just means that, hey, your core is accreting gas and it's capturing it that's within somewhere in the disk. And so here's the basic idea. The larger the mass, well, the stronger the gravitational pull. So therefore, you're able to accrete as a planet more gas. However, the catch is that when you have a planet forming within the solar system, you have to do this in a very short amount of time. And I say this relatively speaking because the time scales that we're talking about here is on the order of about 10 million years. So in the human time scale, that's a long time. But when it comes to how long objects form in the universe, that's actually a blink of an eye. So it doesn't last very long. And the reason for why that is because in the very center of your disk, your star, your sun in our case, is on the process of becoming more and more stable. And during this process, the sun periodically ejects out these very strong solar winds that propels material outward, away from the star, and also effectively away from the planets. So what the planets have to do is they have to accrete as much gas as possible before all of that stuff is blown away from the star in the middle. Okay, so Jupiter was the first of the Jovian planets to form. So Jupiter is so huge that you can actually fit over 1,000 Earths inside of it and then put 10 Earths across its diameter along the equator. And so Jupiter, because it's the closest to the frost line, it was able to accrete so much gas, and it was able to accrete 300 Earth masses worth. So, and the reason for why that is also is because Jupiter's core is as massive as about 10 Earth masses. So you have that much gravity, very close to the frost line, so it was able to accrete a whole lot of mass. And now, if you think about it, Jupiter's core is about the same size as the Earth, but 10 times more massive. But then Jupiter itself, as a planet, is large in size, so it's mostly made up of gas. So what you're seeing actually in this picture is just mostly gas. And that means Jupiter doesn't really have a real surface. So if you were to ever get pulled in by Jupiter's gravity, you'll just keep falling and falling and falling towards the center until you finally hit that solid core right in the middle. Okay. So after Jupiter, Saturn came next, and you guys know Saturn. It's very distinct because of its rings. And so Saturn, about 9 AU away from the sun, it was also able to form a core that is about 10 times the mass of the Earth itself. However, because it's further away from the sun, there wasn't as much gas available in that region in the disk. So it was only able to pull in 80 Earth masses worth of gas and ice. And then after that came along the two ice giants, Uranus and Neptune. And so Uranus and Neptune, they're about, like, size speaking, they're about 4 times the size of the Earth. And then when it comes to mass, they're about 14 to 15 times the mass of the Earth. And they form last because they're like located in the outskirts of the solar system, which means, again, there's less gas there, but also because particles are further away from each other, it's going to take a whole lot longer for them to form, okay? And so instead of being composed mostly of gas, they're actually composed mostly of ice because now they're in the region where you have a lot of these hydrogen compounds being able to condense. And so the reason why Uranus and Neptune are actually blue is because they have methane in their atmospheres. And when you have methane in your atmosphere, methane actually absorbs all white light except for one wavelength, which is blue light. And so blue light is actually reflected outward, which gives Uranus and Neptune this bluish color. And of course, you know, the popular joke, methane comes from cow farts, Uranus, you get the idea. Okay. So we talked about the gas giants and the ice giants. Now what about for terrestrial planets? Does gas capture also work for terrestrial planets? Well, yeah, actually, I mean, if you have mass, then you have gravity, and then if you have gas around you, then you should be able to pull in some of that gas. So gas capture was actually the main process of how the terrestrial planets gained their first or their early atmosphere. And so the thing is that, you know, this first atmosphere was composed mostly of hydrogen and helium gas. However, because these terrestrial planets were so close to the sun, where the temperatures were much hotter, that will cause the hydrogen and the helium gas to move faster within the planet. And if they move fast enough, because of these high temperatures, they could be moving fast enough such that they will actually exceed or be faster than the escape speed, which is, you know, the speed required in order for you to kind of overcome the pull of gravity coming from the planet. So therefore, none of the terrestrial planets were actually able to hold on to their first atmosphere or their only atmosphere. So if you think about Mercury, for example, and Mars and Mercury barely, if any, that they have an atmosphere because they were not able to hold on to this early atmosphere. Um, you have planets, however, like the Earth, that was able to form a secondary atmosphere. And so the secondary atmosphere was primarily due to the geological activity from volcanoes. You have outgassing from volcanoes, and you also have impacts coming from comets on the Earth's surface, which releases, water. And so these molecules that are going to be found in a secondary atmosphere are much heavier than hydrogen and helium. And so therefore, if you have molecules that are heavier, then they're less likely to escape the planet's gravity, even at high temperatures. So if a terrestrial planet does have some sort of atmosphere, it will be a secondary atmosphere. Another example of that is Venus, by the way. Venus has a very thick layer of carbon dioxide. And, that's actually the prime example of how climate change works, because Venus is enveloped in this carbon dioxide layer that it caused the temperature to rise because none of the heat can actually escape from within the planet. Okay, so when all is said and done, if you look around our solar system, it looks amazingly clean and organized. Okay, it's almost like it was cleaned up. And so there's not much debris when you're looking around within our own solar system. And so that comes from two main modes of getting cleaned up. So basically, you have the young sun that is able to produce these strong solar winds that propagate outward, driving away, any kind of lighter materials like gas and dust. And so this happens when the sun was first forming. And, sometimes we like to just call it like the solar baby burps. It's like when the sun was first a baby, then it would like keep burping away all of this material outward. And then the second mechanism, that's the word I was looking for, a mechanism, is when planets are orbiting, they're also able to accrete more material via gravitational forces. So that leads up to more collisions, and then from those collisions, they're able to retain some of that material, cleaning up their orbits, so leading to a more quote-unquote organized solar system. And then when you look around other solar systems that are still currently forming, then we actually observe these bubbles and cavities within these young stars. And essentially what that is that that's basically like the strong wind that's propagating outward produced by the star. Okay? And that's an observed thing. This is a picture that was observed by Hubble. And so you can see that the cavity is here at the very center. And again, that comes from the star in the middle, blowing all of that gas and dust away. Okay, all right, so that's about it for this lecture series. So the next topic that we're going to be addressing is being able to detect other planets in other solar systems. Basically, the search for extrasolar planets. Okay? All right, see you next time.